Hello, everyone. My name is Terry Chen. I'm a Senior Applications Support Scientist at TA Instruments. I would like to welcome you and thank you for joining me for this online training course. Our today's course is Part 2 for Rheology Theory and Applications. This section will be approximately 1.5 hours long. At the end of the course, we will give you a link to download the slides and also an email for asking questions. Here is the agenda for what we will be covering today. First of all, we would like to have a recap on all of the available rheological test methods, which include flow test to measure viscosities and oscillatory test to measure viscoelasticities. And then we're going to discuss rheological applications to varieties of different kinds of materials. Specifically, we'll talk about rheological applications in measuring structured fluid that include low viscosity liquid samples, semi-solid samples, and soft gels. And then we're going to talk about rheological applications in measuring polymers, which include polymer melts, reactive polymers like thermosetting polymers, and also solid polymers. First of all, let's remind ourselves on what rheology measures. Like we have discussed earlier in Section 1, we have talked about rheology can measure samples' viscosity, elasticity, and also viscoelasticity. If your sample is liquid and pourable, you can use rheology to measure its viscosity. If your sample is a purely solid material, then you can use rheology to measure its elasticity property. Most of the materials we're handling on our daily basis can vary from semi-solid to soft gels. Those materials have both viscous response and also elastic response. For those samples, you can use rheology to study their viscoelasticity properties. This slide summarized all common flow test methods for measuring viscosity of liquid samples. You can perform a single point measurement just to measure viscosity at one single shear rate. You can also conduct a continuous ramp experiment to scout samples' viscosity over a wide shear rate range. The most commonly used test method to measure samples' shear viscosity as a function of shear rate or shear stress is called stepped flow or steady state flow. In addition to that, you can also perform viscosity measurement as a function of temperature. Here is a summary of all common oscillatory test methods you can use to study your material's viscoelasticity property. You can set up a strain sweep to measure your sample's linear viscoelastic region. You can set up a dynamic time sweep to measure your sample's property change as a function of time. The oscillation frequency sweep is very commonly used to measure polymer melts or some soft solid material to differentiate materials batch-to-batch variation. In addition to those, you can also program oscillatory tests as a function of temperature. You can either conduct a temperature ramp measurements or you can conduct a temperature sweep measurements. Now we have learned the basic theory of what is rheology, how rheometer does to perform rheological measurements, and also we have learned how to program all of the different kind of rheological test methods to measure the viscosity and viscoelasticity of your sample. Now let's talk about rheology applications. How do we use rheological test results to help you with your research? In this first section, we're going to talk about rheological applications to structured fluid and soft solid. Let us start from the simplest sample first. How do we use rheology to study the viscosity property of a low viscosity Newtonian liquid? First of all, what geometry we shall use? Since this sample has low viscosity, you need to consider to use a larger diameter, large size geometry, such as 60 mm or 40 mm Conan plate or parallel plate. The concentric cylinder with a cup and rotor geometry is also highly recommended. The reason we need to choose a larger diameter or large size plate is because we need to increase the contact area between the sample and the geometry so that we can increase the signal to noise ratio. Regarding test method, this kind of sample's viscosity is independent of your measurement shear rate or shear stress. So when you conduct an isothermal testing, you will see the viscosity of this material is only one number. It is independent of your measurement shear rate. So the most popular test method to study the property of this kind of sample is a flow temperature ramp experiment. So in this test, you are studying the sample's viscosity as a function of temperature. Then, what about non-Newtonian low viscosity liquids? Since this sample still have low viscosity, you still need to consider to use a larger diameter parallel plate and Conan plate geometry. Regarding test method, because this kind of sample is non-Newtonian, the viscosity of this kind of sample will be depending on your measurement shear conditions. So here is an example of showing you the viscosity curve of your eyedrop sample over a wide shear rate range. The information you can obtain from this result is what is the viscosity of this eyedrop sample looks like over the shear rate as you're blinking your eye. The example on the right side is showing you the viscosity curve of two different kinds of cough syrup formulations. From these results, you can see that under high shear conditions, these two formulations shows similar viscosity. But under low shear rate, the viscosity of these two formulations are significantly different. From these results, you can actually predict that which formulation will potentially do a better job to coat your throat. Now, let's move on to test something more complicated, a multiple phase complex system. This kind of sample consists of a continuous phase, such as water or oil, and a dispersed phase, things like a solid particle, oil droplets, or air bubbles. In order to stabilize the dispersed phase, prevent phase separation, you need to add a third component to the system. The third component is kind of like a stabilizer or some associative thickeners. These components are typically some kind of polymeric materials, which can form a weak three-dimensional network structure that can hold those particles, prevent them from undergoing phase separation. Therefore, we call this kind of samples as structured fluid samples. The type of structured fluid can be separated into three major categories. If you have solid particles in a Newtonian liquid, people call that a suspension. If you have one liquid phase into another liquid phase, it is called an emulsion. If you have air bubbles into a liquid phase, and then you can call those samples as foam. Examples of structured fluid include varieties of different materials we're handling in our daily basis. Things like paints, coatings, inks, adhesives, personal care cosmetic materials, and foods. The physical properties of a structured fluid can be quantitatively measured using a rotational rheometer. First of all, these kind of samples are non-Newtonian. Most of the structured fluids behaves shear thinning. Some of those highly filled systems may also show shear thickening behavior. Structured fluids shows a certain yield stress and also behaves thixotropic. At rest conditions, structured fluid may also exhibit a certain amount of elasticity. Here is a schematic showing the physical behavior of a typical structured fluid sample. At rest conditions, this sample shows a weak three-dimensional network. All the particles are stabilized there without no phase separation. So therefore, at these conditions, the sample shows high viscosity and also exhibit certain elasticity. As you conduct a shear to this sample, especially as you're gradually increasing the shear stress up to a certain critical value, this three-dimensional network structure is destroyed. That is called you pass the yield stress of this material. After the structure is destroyed, sample starts to flow. All the particles start to align towards the shear direction, which eases the flow. That causes the sample to show shear thinning behavior. when you remove the shear away from the sample, a structured fluid sample takes a certain amount of time to recover its structure back to the weak three-dimensional network. Parallel plate geometries are commonly used to test this kind of structured fluid. The commonly used parallel plate size varied from 40 mm down to 20 mm in diameter. In order to avoid slippage during the measurement, a roughened surface parallel plate is also recommended. Typical roughened surface geometries include a crosshatch plate or a sandblasted plate. In addition to use parallel plate geometry, a concentric cylinder cup with a vane rotor or helical ribbon rotor is also commonly used for testing structured fluid. All of these geometries can help efficiently prevent slippage to occur during the measurement. Since structured fluid containing particles, you need to be very careful when selecting to use a cone plate geometry for the measurements. As we have discussed before, when you use a cone plate geometry, you are not allowed to freely change the measurement gap. The gap must equal to the truncation height of this particular cone geometry. Depending on the cone angle, the truncation gap of a cone geometry will vary between 10 to 120 microns. So now, if you have large particles in your structured fluid sample, using a cone plate geometry, you may end up just grinding the particles, not really measuring the bulk property of the whole system. In this case, a parallel plate geometry is more recommended because you can freely adjust the measurement gap. A typical measurement gap for using a parallel plate geometry varied from half a millimeter all the way up to 2 millimeters. This figure shows a general viscosity behavior of a typical suspension sample. Under low shear conditions, the three-dimensional network structure inside the sample is strong enough to hold the particles, prevent the particles from settling or undergoing phase separation. So therefore, under low shear rate condition, this sample shows high viscosity. As you gradually increasing shear rate or shear stress, especially when the shear stress is high enough to break down this three-dimensional network, sample starts to flow. All the particles start to align towards the shear direction, which eases the flow. That causes the sample to show shear thinning behavior. As you further increasing shear rate, up to a certain shear rate conditions, the hydrodynamic interactions will push the particles out of the alignment. From there, some temporarily formed hydroclusters will cause those particles from bumping to each other. That will cause the sample to show shear thickening behavior. On TA Instruments website, we have a very helpful webinar talking about rheology of colloid. If anybody who's interested to learn more about this topic, please feel free to get onto our website and take this webinar. Sometimes people like to ask this kind of questions. If I like to study the viscosity property of my sample, then what shear rate should I use? The answer to this question is, it is all depending on what is the goal of your measurement. If your goal for viscosity measurement is to correlate and predict your sample's storage stability, then you should perform the measurement at low shear rate range. The viscosity measured under low shear rate can be used to directly correlate to your sample's storage stability, how stable your sample is to prevent sedimentation or settling. If your goal is to measure your sample's viscosity that correlates to a specific applications condition, then you should really try to find out the shear rate that mimic your applications conditions. For example, if you would like to measure your sample's shear viscosity under Truing conditions, and then you should be focusing on a moderate shear rate, somewhere around a few reciprocal second to a tens or 20s reciprocal second. If you would like to measure your sample's viscosity that correlate with a high-speed coating condition, and then you should really focus on measuring sample's viscosity under high shear rate. This is an example of showing the viscosity scan results on two water-based adhesive formulations. the blue formulation behaves more shear thinning, and the red formulation behaves more Newtonian. So under low shear rate, the blue formulation exhibits much higher viscosity compared to the red formulation, which indicating that the blue formulation will potentially have much better storage stability. Under moderate shear conditions, which correlates to transportation or mixing or stirring, both formulations shows similar viscosities. But under high shear coating application conditions, the blue formulation exhibits much lower viscosity compared to the red formulation. That tells you that this blue formulation is a lot easier to use, easier to spread to a thin layer. As we have discussed before, all structured fluid samples exhibit a specific yield stress. Then what is yield? Yield stress is a time-dependent characteristic. It is associated with many structured fluids such as mayonnaise, ketchup, shampoo, or lotion. A material that has yield does not flow until the applied stress exceeds a certain value, which is the yield stress. Yield stress is purposely created in formulation by adding some additional associative thickener. Yield can help to stabilize your sample. It can help to avoid sedimentation and increase your sample's shelf life. Yield stress can help to reduce any flow under gravity and also stabilize your flow against vibration. Yield can be quantitatively measured using a rotational rheometer. Here, we would like to introduce 4 commonly used methods for yield stress analysis. They are a shear stress ramp, a shear rate ramp, a shear stress sweep, and a dynamic stress sweep or strain sweep. But please note, yield behavior is a time-dependent characteristic. So the measured yield stress value will vary depending on your particular experimental parameters. So when testing a whole series of samples, you need to stay with the same test method and same test parameters. The continuous stress ramp is the most commonly used method for yield analysis. In this measurement, stress is ramped from 0 until the sample starts to flow. During the measurement, sample viscosity and shear rate are monitored as a function of time. Here is an example of measuring the yield stress of a body lotion sample. In this test, the sample is loaded between a 40 mm sandblasted parallel plate. Shear stress is ramped from 0 up to 200 pascals in 60 seconds. After the test is finished, we plot viscosity versus shear stress in linear scale. Yield is determined at the point where viscosity shows a peak. So as we can see from these results, under these particular test conditions, the yield stress of this particular body lotion sample is observed at 27 Pascal. Alternatively, you can also consider fit your experimental data with a flow model that has yield stress term. These following 3 flow models, the Bingham model, the Hershey-Buckley model, and the Caisson model, all contains a term in their equation to describe yield. Using this curve fitting, you can extrapolate your experimental stress versus rate curve down to shear rate equals to 0, and that is the yield stress of your sample. Here is an example of measuring the yield stress of ketchup. At the beginning of the test, the sample did not flow. As we increasing the shear stress, shear rate did not seem to change much. But as we further increase the stress and the stress is passing the yield point, ketchup starts to flow. After that, the increase of the shear rate is almost linearly proportional to the increase of the stress. This behavior seems to have a good fit with the Bingham model. So if we fit this flow curve with the Bingham model, extrapolate the stress shear rate curve down to the point when shear rate equals to 0, Then from these results, we can calculate the yield stress of ketchup, which is roughly at 58 Pascal. The second method people use for yield stress analysis is this shear rate ramp down method. This is a very commonly used method to study the yield stress of very low viscosity liquid samples. We all know that orange juice or this kind of orbit drinks, they have very low viscosities. Their viscosities are close to the viscosity of water. But low viscosity solution can also contain a yield stress. As we can see, orange juice is not transparent, so it contains fibers and pulps. To stabilize this system, people have to add stabilizers or some associative thickeners, such as some natural polysaccharides. Those polymers create a very weak microstructure to prevent the orange juice from phase separation. Using this shear rate ramp down method, we can quantitatively measure this low yield stress. After we load the sample to the rheometer and conducting this shear rate ramp down method, initially we can see that stress decreases with decreasing shear rate. But when the rate decreased down to a certain value, the stress curve shows a plateau and did not further decrease with rate. And then we can take the slope stress and define that as the yield stress of this sample. Below yield, the viscosity of the sample goes to infinite with a slope of -1. Another method for yield measurement is the steady-state stress sweep. In this test, stress is increased stepwise on a log scale. At each step, the sample viscosity is measured only when the equilibration has been reached. Yield stress is identified by taking the onset value from the viscosity versus shear stress curve. Here is an example of testing the yield stress of a toothpaste sample using this steady-state stress ramp method. Stress is swept from 10 Pascal to 500 Pascal. From these results, we can see that under low stress, toothpaste shows really high viscosity. As we gradually increase the stress, especially when the stress is close to about 100 Pascal, within a very small change in stress, you can observe that all of a sudden the viscosity of toothpaste drops several decades. This is indicating that the stress is passing the yield of the toothpaste and the sample starts to flow. From these test results, we then take the onset value from this viscosity versus stress curve. From the results, we can identify that the yield stress of this particular toothpaste is observed at about 102 Pascal. When testing viscosity and yield stress of samples such as toothpaste, wall slip is often observed. Wall slip is the slippage that occurred at the interface between the sample and the surface of the geometry. So when slippage occurs, it always shows some artifact results. Here is an example of testing the viscosity and yield stress of a toothpaste using two different kinds of geometries. The green curve shows the flat surface geometry results. The results shows that at the stress greater than 18 Pascal, sample shows 1 yield stress. After that, sample behaves shear thinning. When the shear stress is greater than 100 Pascal, it's showing a second yield. But if you perform the same measurement using a roughened surface crosshatched geometry, you will prove that actually the first yield observed at 18 Pascal is the artifact that was caused by slippage at the interface. So the true yield stress of this particular sample should be at a shear stress greater than 100 Pascal. The last method we would like to introduce for yield analysis here is under dynamic mode. This is a dynamic strain sweep or stress sweep test under a constant frequency. From this measurement, yield stress is identified by taking the onset point of a storage modulus versus oscillation stress curve. This method is good for measuring the yield stress of some high viscosity samples, those samples that may slip in a flow type of measurement. Here is an example of testing the yield stress of a mayonnaise sample and at a frequency of 1 Hz. Yield stress is observed at a stress of about 53.8 Pascal. This is also a critical stress which is described as the end of the linear viscoelastic region. Beyond this point, sample will undergo an irreversible plastic deformation. Here is a case study of using string sweep experiment to compare the stability of two cosmetic cream samples. From this measurement results, you can see that the yellow formulation shows slightly higher modulus compared to the blue formulation. However, this string sweep measurement result shows the yellow formulation has much shorter linear viscoelastic region. When the oscillation strain is greater than no more than 1%, the modulus of this formulation shows significantly decrease, which means the structure of this formulation is breaking down. So from this measurement results, you can potentially predict that the yellow formulation, even though the gel is slightly firmer, but it shows poor stability against any vibration. As we have discussed earlier, a structured fluid has a yield stress, and it also shows a syncotropic behavior. So what is synchrotropy? Synchrotropy is a time-dependent shear thinning property, which is used to characterize structure change reversibility. A syncotropic fluid takes a finite time to attain equilibrium viscosity when introduced to a step change in shear rate. Synchotropy is a desired property for many applications, such as controlling sagging or leveling of paints, startup of a pipeline flow after rest. Synchotropy can be quantitatively measured using a rotational rheometer. Here, we would like to introduce 4 commonly used methods for syncotropic analysis. These methods are stepped flow method, a stepped dynamic method, stress ramp up and down method, people also call that syncotropic loop testing, and last, a pre-shear followed by a time sweep method. But please note, syncotropic behavior is a time-dependent characteristic. So the measured syncotropic index value will vary depending on your experimental parameters. So if you would like to analyze the syncotropic properties of a series of materials, please stay with the same test method and same testing parameters. Traditionally, people like to use a stepped flow method to quantify synchotropy. This procedure contains 3 steps. In the first step, sample's viscosity was measured under low shear rate, for example, at shear rate of 0.1 reciprocal second. This low shear viscosity represents sample status at rest condition. And then, in the second step, increase the shear rate by at least the magnitude of 10 times or even greater than 10. During these measurements, the microstructure of the sample is destroyed. Sample's viscosity is decreased significantly. In some literatures, people like to take the ratio of the low shear to high shear viscosity and describe that as the syncotropic index of the sample. In step number 3, the measurement jumped back to low shear again. The recovery of sample's viscosity is monitored as a function of time. This third step is to measure the syncotropic recovery. Here is an example of measuring the synchrotropy of a blue paint. This paint is very shear thinning. At low shear conditions, at shear rate of 0.1 reciprocal second, it shows high viscosity. But when the shear rate is increased up to 10 reciprocal second, the viscosity decreased almost 2 decades. In the third step, when shear rate drops back down to 0.1 reciprocal second again, this blue paint takes certain time to recover its viscosity back to a high value. This recovery time is critically important to its application's performance. If the recovery time is too short, you will end up get some leveling issue in application. So when you use this paint, you will end up get some roughened surface. But if this recovery time is too long, you will have some sagging issues when using this paint. Instead of doing a 3-step flow test, people also use a 3-step dynamic oscillatory test to measure thixotropy. In the first step, a dynamic time sweep is conducted using a strain that's in the linear viscoelastic region of the sample. The modulus measured in this step represents to the sample structure at rest condition. And then in second step, apply a large amplitude oscillatory shear to the sample using a large strain for the measurements. This measurement is to destroy the microstructure of the material. Then when we jump back into third step, we're using a small amplitude again to perform time sweep. During the third step, the time it takes for the sample to recover its structure is monitored as a function of time. This method is good for testing some of those high viscosity samples, those samples that may slip in a flow type of measurement. Here is an example of measuring the same blue paint using this 3-step oscillatory method. When testing this paint using a small strain that's within its linear viscoelastic region, the results show that G' is greater than G double prime, which indicate that this paint contains a structure and behaved like a solid at rest condition. As the oscillation strain increased up to 100% in step number 2, the structure of the paint is destroyed, and the result shows that G double prime is greater than G prime, which means the sample structure is destroyed and now it behaves liquid-like. And then, as we step back to using a small strain again, in step number 3, we monitored how long it takes for the sample to recover its structure. So from the results, you can see that it takes a certain amount of time for both moduli to increase back up. And there is this G crossover, which indicates that sample undergo a liquid to solid transition. After that, G prime starts to become greater than G double prime. That tells you the sample structure is gradually recovered as a function of time. Another method people use to quantify thixotropic index is by doing a thixotropic loop test. This is a shear stress or shear rate ramp up and down method. For example, we can ramp shear stress linearly from 0 up to 100 Pascal in 1 minute, and then ramp the stress back down from 100 to 0 in another minute. If the sample is thixotropic, then the ramp up and ramp down curve will not overlay. Thixotropic index is calculated from the area between the up and down curve. However, since the operator can alter the ramp up and down time, so the measured thixotropic index value may vary depending on the stress ramp speed. On TA Instruments website, there is a short YouTube video that teaching people how to set up this thixotropic loop experiment and how to analyze thixotropic index using Trails software. Here is a case study of using this loop method to test the thixotropic index of 3 food samples: mayonnaise, yellow mustard, and ketchup. These 3 samples were measured using a 40 mm sandblasted parallel plate geometry at a gap of 1 mm. Shear stress was ramped from 0 to 100 Pascal in 1 minute, and then ramp it back down to 0 in another minute. As we can see from the first ramp test results, all 3 samples shows similar yield stress, which shown at about 60 to 70 Pascal. But after yield, they show very different thixotropic properties. The ketchup is much more thixotropic compared to mayonnaise. The thixotropic index is quantitatively calculated from taking the area between the up and down curve. Another method people use for monitoring syncotropic recovery is a pre-shear followed by a dynamic time sweep method. Apply a constant shear to the sample for a certain amount of time to break down the structure. And then, after that, immediately start a dynamic oscillatory time sweep using a small strain that's within the linear viscoelastic region of the sample. During the time sweep, the sample modulus is measured over time. It is a monitor of the structure recovery as a function of time. Here is the case study results of testing the same blue paint using this pre-shear followed by time sweep method. After pre-shear at 100 reciprocal seconds for a minute, the structure of this paint is destroyed. And then immediately you start a dynamic time sweep using a small strain that's in the linear viscoelastic region. During the measurement, storage modulus change as a function of time is monitored. So fit this curve to a equation. So use this equation, you can then calculate the structure recovery time. This recovery time is critical in controlling the performance of the paint sample. So far, we have already talked about how do we study the non-Newtonian property of structured fluid, how do we measure yield stress, and how do we quantitatively study the syncotropic behavior of structured fluid. At last, let's talk about how do we design an experiment to measure elasticity of a structured fluid. The three commonly used test methods to determine viscoelasticity property of a structured fluid include a dynamic frequency sweep, a creep recovery experiment, and also a normal stress measurement using a specific cone plate geometry. Among these three methods, the dynamic frequency sweep test is the most popularly used method to evaluate and compare the viscoelasticity property of structured fluid sample. Here is a case study results of evaluating the viscoelasticity property of a cosmetic lotion sample using dynamic frequency sweep. From these results, you can see that the sample's storage modulus is greater than loss modulus. That indicates that this lotion sample exhibits a solid-like behavior. But both moduli are slightly increasing with your increasing measurement frequency. That tells you that the structure of this lotion sample is not very stable. It is frequency dependent. And during the measurement, you are able to also get the complex viscosity information. This result shows that this lotion sample behaves very shear thinning. Tangent delta is also a very popularly used parameter to quantify viscoelasticity of a lotion sample. Lower tan delta means the sample behaves more elastic. A higher tan delta means the sample behaves more viscous and less elastic. These slides provide a good summary of using frequency sweep method to evaluate viscoelasticity property of varieties of different samples. If your sample is mostly Newtonian, very liquid-like sample, in the frequency sweep test results, you will see that loss modulus is greater than storage modulus. That tells you the sample is liquid-like. Both moduli shows kind of like a straight line, with the loss modulus shows a straight line with a slope of almost -1, and storage modulus shows a straight line with a slope of almost -2. In the meantime, if you plot complex viscosity as a function of measurement frequency, you see that the viscosity shows almost Newtonian behavior, which means complex viscosity is independent of your measurement frequency. For a semi-solid material like a polymer melt, silly putty, or like a soft cream, during this frequency sweep measurement, you may observe a G' and G" crossover. So that tells you that within your measurement frequency window, sample could behave either solid-like or liquid-like. And then if you study the viscosity of the sample as a function of oscillation frequency, you see that initially sample shows some Newtonian plateau and then it shows shear thinning behavior. Using a frequency sweep to measure a weak gel sample, like a lotion, like a mayonnaise, so the measurement results will look like this. storage modulus will be greater than loss modulus, but both moduli are not independent of the measurement frequency. That tells you this gel-like structure is frequency dependent. And in the meantime, the complex viscosity versus frequency sweep shows that this kind of weak gel sample are extremely shear thinning. If you're talking about a more stable gels, like a gelatin gel, okay, when you perform the frequency sweep measurements, you will see that storage modulus will be greater than loss modulus, but both moduli are more or less independent with your measurement frequency. That tells you that this gel sample within the measurement frequency range is relatively stable. And of course, for this sample, it is showing extremely shear thinning behavior as well. Next, let's talk about how do we use rheology to study the viscoelasticity behavior of a soft solid material. Hydrogels and creams are widely used in varieties of applications, including some tissue engineering, wound patch, drug delivery, or some biomedical devices. Rheology can provide useful information to evaluate the rheological physical behavior of a soft solid material. Rheology measurement can help to quantitatively measure the gel strengths and also compare their elasticity. If you log on to TA Instruments website, you should be able to find a lot of very helpful application notes, some short papers that's talking about how do we use rheology or even also use DMA to evaluate the viscoelastic property of soft solid or gel samples. Here is a case study of using rheology to study viscosity or viscoelasticity property of a hyaluronic acid solution or hyaluronic acid gel sample. Hyaluronic acid is a natural polysaccharide polymer, which is commonly used in pharmaceutical, biomedical, or personal care industries. Rheology can be used to quantitatively evaluate the viscosity and also viscoelasticity properties of this hyaluronic acid solution or gels. First of all, hyaluronic acid is water-soluble. You can make a water solution of hyaluronic sample and study its viscosity behavior. From the measurement results, you can actually quantitatively compare different batches of hyaluronic acid, the differences in their molecular weight. When you add a cross-linking agent to this solution, you can then, using a dynamic time sweep, to monitor how fast the solution forms a hydrogel. A time sweep can be used to monitor this whole gelation process. After the gel is formed, you can then, using a dynamic frequency sweep, to quantitatively compare different concentration or different batches of hyaluronic acid gel strengths. The correlation you can do is by comparing the differences in their storage modulus. This frequency sweep results shows that hyaluronic gels are very strong gels, very viscoelastic, and the gel strength is more or less independent with your measurement frequency. Another case study here is to study the gelation of a thermally reversible gelatin gel. We know gelatin solution can form a gel at low temperature, but this gel will melt at a temperature greater than 40 degrees. So in this analysis, we load this gelatin solution at a temperature around 50 to 60 degrees C, and then conducting a temperature ramp down experiment. So with this measurement, we can monitor at what particular temperature this gelatin solution will form a gel. So after the gel is formed, we can also conducting a temperature ramp up experiment to see with different heating rates at what temperature the gel starts to melt. The dynamic frequency sweep test can be used to compare the gel strengths at the application's temperature. Here's the results of showing frequency sweep testing at 10 degrees C with gelatin at different concentrations. From these results, we can see that with gelatin concentration at 1%, during this measurement, G double prime is greater than G prime. That tells you that at 1% concentration, gelatin cannot form a gel even at 10 degrees Celsius. So from the concentration of 2% and above, G prime is greater than G double prime. That means at those concentrations, the gel can be formed at 10 degrees C. with higher concentration, G prime is showing higher. That means the gel is getting stronger. This is a case study of using frequency sweep experiment to evaluate and compare the differences of elasticities on two different kinds of contact lens sample. The frequency window we're selecting here matches the speed of how fast people blinking their eyes. Tangent delta is the parameter that we use to quantitatively evaluate the difference on their elasticities. From this measurement, you can see that the sample B, the elasticity of sample B, is more independent of your measurement frequency. In order to avoid evaporation during your measurement, you can choose to use the submerged accessory, perform the measurement under buffer condition. Another case study we would like to discuss here is how do we use a stress relaxation experiment to study the physical property of an eye patch gel. A stress relaxation test can be used to measure how much stress a gel can hold at a given deformation. Particularly from these results, you can see that this is how much stress this gel patch can hold at a specific given strain, varied from 10% up to 100%. In addition to study viscosity and viscoelasticity of a sample using a rotational rheometer, we also provide with our users some tribology accessories. Those accessories allows you to quantitatively measure the coefficient of friction. These accessories include a ring-on plate, ball on 3 plate, ball on 3 ball, and also 3 balls on 1 plate. Here is a case study of measuring the coefficient of friction of 4 different kinds of lotion samples on the surface of skin. If anyone who is interested in this topic, we have 2 very helpful tribology webinars on TA Instruments website. Please consider log on to our website and take those webinars. So far, we have discussed rheology applications in measuring liquid, semi-solid, and soft gel samples. In this next section, we're going to discuss rheology applications in measuring polymer materials. Specifically, we're going to talk about how rheology is used to measure polymer melts, reactive polymers, and solid polymers. In polymer industries, rheology technique is commonly used for 3 major purposes. First, the rheological testing results can be used to quantitatively compare and evaluate the polymer chain's molecular weight distribution, and also compare polymers which containing different amount of long chain branching structure. Secondly, rheological testing results can be used to guide polymer processing, such as extrusion or blow molding. And the third purpose for rheological testing is to evaluate the performance of an end-use product. A specific rheological measurement results can be used to quantitatively compare the sample's mechanical strength, toughness, measure sample's glass transition, and also dimension stability. Here is a list of all commonly used experiments for polymer analysis. They include oscillation measurements, flow measurement, and creep recovery measurements. Among all of these procedures, dynamic oscillatory tests are most commonly used. The time sweep experiment is typically used to evaluate your sample's thermal stability at processing conditions. Strain sweep is used to evaluate the linear viscoelastic region of the sample. Dynamic frequency sweep experiment is the most popularly used method to evaluate the properties of polymer melts or even solid polymers. The measurement results are sensitive to polymers' molecular architecture, which are molecular weight distribution, and also long chain branching. Dynamic temperature ramp and temperature sweep experiments are commonly used to evaluate the physical property of an end-use polymer material. Then, what geometry we shall use to measure polymers? If you want to measure the rheological property of polymer melts, then this 25 and 8 mm parallel plates are the most commonly used geometries. If your goal is to monitor thermal setting polymer curing, you need to select to use a disposable parallel plate. At TA Instruments, we provide with our customers varieties of different sizes of disposable plates. The diameters varied from 8 millimeter, 20 millimeter, 25 millimeter, all the way to 40 millimeter. If your goal is to measure the normal force on polymer melts under shear conditions, then you need to use a large angle Conan plate geometry. For Aries G2 user, if anyone who is interested to conduct large amplitude oscillatory shear measurements, in order to avoid edge fracture to occur at lower strains, you can also consider to use this cone partition plate. To measure the rheological property of polymer solid sample, you can either choose to use torsional rectangular geometry and torsional cylindrical geometry to measure sample moduli under shear deformation mode, or choose to use one of these kind of DMA clamps to conducting DMA type of measurements. For polymer melt analysis, the very first test you should consider to do is actually a dynamic time sweep. This time sweep helps you to determine your sample's thermal stability under your processing temperature. Here is an example data of testing polypropylene melt at the processing temperature of 230 degrees C. From this measurement results, you can see that the viscosity of this polymer melt is decreasing over the measurement time, which indicating that this polymer is not very stable and is degrading. The other example on the right side is showing the time sweep measurement results on a high temperature PEEK polymer at its processing temperature of 400 degrees C. This result tells you that if you're processing PEEK polymer under nitrogen atmosphere, over 30 minutes of the processing time, the sample could more or less remain stable. But if you switch to use an air atmosphere to processing the polymer, so within a half an hour, you see the sample's modulus significantly build up. It undergoes a cross-linking reaction. Understanding the viscosity of polymer melt is important because polymer melt's viscosity as a function of shear rate can be used to correlate to polymer's molecular architecture and also can be used to guide polymer processing. The viscosity of a polymer melt measured under low shear rate, especially when it's extrapolated down to zero shear viscosity, and this value can be used to quantitatively calculate polymer's molecular weight. The viscosity measured under moderate shear rate range is such as from a few reciprocal second to a few hundred reciprocal second is used to guide some specific polymer processing like compression molding or extrusion. The viscosity measured at high shear rate is correlates to some special polymer processing such as blow molding or injection molding. However, since polymer melt is viscoelastic, conducting a flow measurements to measure the viscosity over a wide shear rate range is very challenging. Edge fracture is typically observed at shear rate no greater than just a few reciprocal seconds. So, which means you will not be able to perform a flow measurements to measure polymer melt's viscosity, especially up to higher shear rate conditions. So in this case, you can consider to go through a Cox-Merz transformation by transforming a dynamic frequency sweep data to a flow data. So in this case, you can extrapolate and extend the measurable shear rate range up to the maximum frequency your instrument can go to, which is roughly 628 reciprocal second. For ultra-high shear rate viscosity measurement, you can use a technique called time-temperature superposition to extrapolate the viscosity information, or you have to consider to select to use a capillary viscometer to conduct the viscosity under these ultra-high shear rate conditions. The zero shear viscosity of a polymer melt is sensitive to its molecular weight. If your polymer containing short chains, which does not have a loss of entanglement, you will see that the measured zero shear viscosity is linearly proportional to its molecular weight. However, if your polymer containing a loss of long chains and also has a loss of entanglement, Then its measured zero shear viscosity follows a power law relationship to its molecular weight. And the power law alpha here, depending on the polymers, this value is varied from 3.4 to 3.6. The K value here is depending on the type of polymers you are analyzing. As we have discussed before, since polymer melts are viscoelastic, so edge fracture always limit the shear flow measurements up to high shear rates. So to study the rheological properties of polymer melts, most of the tests are conducted under oscillatory mode. Specifically, frequency sweep is the most commonly used method for studying polymer melts rheology. Here is an example data of showing 4 different polymers, SPR polymers, their frequency sweep measurement results. After the test is finished, you can plot sample's complex viscosity as a function of frequency. From these results, you can see that for polymers that has higher molecular weight, it's showing higher zero shear viscosity. So the relationship between zero shear viscosity versus molecular weight almost follows this linear relationship in log-log scale. Also, in the frequency sweep results, most of the time you will observe that the G' and G" curve will show a crossover. This G crossover frequency is very sensitive to polymers' molecular weight. So when conducting a frequency sweep test on a series of polymers that has different molecular weight, you will see that for polymers that shows lower molecular weight, we'll have this G crossover occurred at higher frequency. And for polymers that has higher molecular weight, we'll show this G crossover at lower frequencies. If anyone who is interested to use melt rheology data to study polymers molecular weight and molecular weight distribution, I would recommend you consider log on to TA Instruments website and take this free webinar that is given by Professor Chris McCaskill. In his webinar, he specifically discussed all of the theories that you can use to quantitatively calculate a polymer's molecular weight and molecular weight distribution. As we have just discussed, in the frequency sweep measurement results, the G', G" crossover frequency is sensitive to polymers' molecular weight. Now look at this test results. These two polymers shows the G', G" crossover almost occurred at the same frequency. This tells you that these two polymers has about the same molecular weight. But the difference is observed at their G crossover modulus. The differences in this G crossover modulus is indicating that these two polymers have different molecular weight distribution. For the polymer that shows higher G crossover modulus means this polymer has narrow molecular weight distribution. For a polymer that shows lower G crossover modulus, that means this polymer has broader molecular weight distribution. Now, let's make a summary of how do we use this frequency sweep experiment, especially use this G crossover point as an indicator to compare polymers that has different molecular weight and different molecular weight distribution. When conducting a frequency sweep measurement on a series of polymers that has different molecular weight and molecular weight distribution, if you observe one polymer that shows higher G crossover frequency, that means this polymer potentially has lower molecular weight. If you observe a polymer that shows a higher G crossover modulus, that means this polymer may have a narrower molecular weight distribution. To compare the differences of polymers with different molecular weight distribution, sometimes people just simply plot the loss modulus as a function of frequency through comparing the shape of the curve, or by taking the peak value of this loss modulus. Use that as an indicator. We can also compare the differences in the broadness of molecular weight distribution. In TRIOS, we have this molecular weight distribution software package. Using this software package, you are able to calculate the molecular weight and molecular weight distribution of roughly 20 common polymer materials. For example, polyethylene, polypropylene, or polystyrene. If anyone who is interested to learn more about how to use rheology to calculate polymers' molecular weight and molecular weight distribution, again, I would like to recommend you consider going to TA Instruments website and taking this free webinar given by Professor Chris McCaskill. Frequency sweep experiment is very sensitive to polymer chain relaxation and polymer chain entanglement. Here is an example to demonstrate how sensitive this experiment is. Here we have a regular polystyrene polymer which has molecular weight of roughly 400,000. When conducting a GPC measurement, this polymer shows a unimodal distribution shape. So in a frequency sweep test, we can see that G' and G" shows a crossover, and the low frequency region, both G', G" curve shows a straight line, and G" shows a straight line with a slope of -1, and G' shows a slope of -2. But when mixing this normal polystyrene sample with 1% ultra-high molecular weight polystyrene, in this case, okay, we're slightly enhance the polymer chain entanglement. In this case, if you conduct a GPC measurement, you barely see that 1% fraction into this whole mixture. But when you conduct a frequency sweep measurements, the measurement results, especially under low frequency region, you see very obvious difference between the G' and G" curve. Now, when you're mixing this regular polystyrene sample with 4% ultra-high molecular weight polystyrene sample, this time in the GPC measurement, you started to see a small bump in here, that indicating that it is measurable in the GPC test method. But now, if you conduct a frequency sweep measurements on this polymer mixture, you will see multiple relaxations. Under low frequency range, you see G', G" undergoes multiple crossovers. This shows that this measurement test method is really sensitive to any increasing in polymer chain entanglement. This is a case study of using melt rheology data to help troubleshooting with processing issues. Here we have two HDPE polymers that we use to make pipes. One batch of polymer is able to make the pipe that has smooth surface, and the other batch is making the pipe that shows roughened surface. So what could be causing the issue? If you just compare the viscosity of these two batches, you barely see that these two batches has much difference. However, if you focus on analyzing the difference using frequency sweep by comparing the storage modulus under low frequencies, you can clearly see the difference. The bad batch that is making pipe that shows rough surface shows much higher low frequency modulus. That tells you that this batch has a lot more elasticity. So the polymer chain has a lot more entanglement. That's why it takes longer time to relax. However, if you look at this good batch, it shows lower low frequency modulus. That tells you this polymer is less entangled, so it is easily to flow flat and create a smooth surface. This is another case study showing how to use a dynamic frequency sweep test results to correlate with the tack and peel performance of a pressure-sensitive adhesive sample. In this frequency sweep results, the storage modulus measured at low frequency can be used to correlate with the tackiness strength of the adhesive. If one adhesive shows higher low frequency modulus, that means this adhesive material has much stronger tackiness. The modulus measured at a high frequency can be used to evaluate and compare the peel performance. If the material shows lower high frequency modulus, that tells you this adhesive is easier to peel. Sometimes, in one single frequency sweep test may not be able to cover the entire frequency range of interest. So in this case, you can consider to use a time-temperature superposition technique to extend the frequency to a much wider range. One of the most commonly used methods for evaluating the tack performance of a pressure-sensitive adhesive sample is described in this ASTM 2979. This test can be conducted on a rotational rheometer using an 8 mm parallel plate geometry. we place the PSA sample between the two plates, apply a certain pressure for a shorter period of time, and then we pull off the plate with a fixed speed, for example, at a speed of 0.1 millimeter per second. The maximum force that is required to pull the plate away is defined as the sample's tackiness. In this type of test, breakings may occur in three different ways. If the bound force at the interface is stronger than the cohesion strength of the adhesive, then breakage will occur between polymer layers. If the cohesion strength is much stronger than the adhesion bound at the interface, then breakage will occur at the plate interface. Sometimes there could be a mix of breakage for both cohesion and adhesion. This figure shows the tack testing results of a non-cross-linked and a cross-linked PSA sample. The cross-linked PSA shows significantly higher cohesion strength due to the introduction of cross-linking network. Therefore, failure occurred at the interface. The non-cross-linked PSA shows weaker cohesion bound, so failure is observed between the polymer adhesive layers. Most polymers are used with fillers. Adding fillers to the polymer will significantly increase its melt viscosity. This figure shows the viscosity curve of a polyethylene sample with and without adding fillers. From this data, you can see that after we mix the polymer with filler, the viscosity is increased. The most obvious difference is observed under low shear rate range. The filler particle-particle interaction causes this polymer melt to show more non-Newtonian behavior and more shear thinning. So the zero shear viscosity of this filled system is significantly increased. The dynamic temperature ramp experiment is commonly used to evaluate the viscoelastic property of a polymeric material. Here, this is a case study of using the dynamic temperature ramp test to evaluate the performance of a pressure-sensitive adhesive sample. These test results provide many important information to the performance of this adhesive. First of all, the glass transition is observed at 16.3 degrees Celsius based on the location of the tangent delta peak. Below glass transition, the sample is hard and brittle and has no tackiness. So glass transition temperature is usually considered as the lowest application temperature of this adhesive. Above TG, the sample softens and the modulus drops significantly. The sample behaves like a viscoelastic material. At high temperature, for a non-cross-linked adhesive material, it will eventually molten. This is observed at the highest G crossover point, which we define as a Tx. Above this temperature, adhesive flows like a liquid and completely lose cohesion strength. So in general, the application temperature window of a PSA sample will be described between the Tg and Tx. In addition to measure transition temperatures, this temperature ramp experiment also provides information on sample's modulus. The rubbery plateau moduli, G', G', measured at the application's temperature is used to evaluate the cohesive and adhesive strength of this adhesive material. If anyone who is interested to learn more about how rheology can help with adhesive industries, we have a very helpful webinar on our website that on this topic. So you're welcome to log on to TA Instruments website and take this free webinar. The dynamic temperature ramp experiment is also used to compare polymers that has different molecular architectures, such as molecular weight distribution, and degree of cross-linking. For example, if you're testing a series of polymer sample that has different molecular weight, you will observe that for polymers that has lower molecular weight will shows a much shorter rubbery plateau region. If you compare polymers which has different molecular weight distribution, you will see differences in the flatness of its rubbery plateau region. For the polymer that has much broader molecular weight distribution will show the modulus decrease in a lot earlier, lower temperature. If the polymer is cross-linked, it will never melt and flow. So the rubbery plateau modulus will remain constant all the way until up to a high temperature when samples start to degrade. The higher the cross-linking density, the higher the measured rubbery plateau modulus. Also, in the meantime, Tg is also observed to increase with increasing cross-linking density. This is a case study of using this dynamic temperature ramp experiment to study the operation temperature window of this hot melt adhesive sample. The sample is loaded at 100 degrees C. From here, we're conducting a cooling experiment with a cooling rate of 3 degrees C a minute. During this measurement, we can see that the sample remains to have certain tackiness until the temperature gets colder than 62 degrees C. Below this temperature, the sample becomes solid-like and completely loses the tackiness. After the sample is completely solidified, we then conducting a heating experiment with a heating rate at the same 3 degrees C a minute. In this heating test, we can observe that in order to melt this adhesive, you need to reach the temperature at least greater than 79 degrees C. For both Aries G2 and Discovery hybrid rheometer users, we provide a special accessory that is called EVF or EVA, Extensional Viscosity Fixture or Extensional Viscosity Accessory. This accessory allows you to be able to measure the extensional viscosity of polymer melts. Many processing flows are elongation flows. Extensional viscosity measurements can be used to help predict polymer processability. This nonlinear elongation flow is more sensitive for polymer chain entanglement, for example, polymer chain long chain branching. This test method is more sensitive compared to use the shear flow test method. Extensional rheology is very sensitive to polymers long chain branching. Here is a study of measuring the extensional viscosity of a linear polymer versus a polymer that containing long chain branching structure. LLDPE is a linear polymer. This is the data shows the LLDPE's extensional viscosity measured at different extensional rate. This extensional viscosity value is equals to 3 times of the steady shear flow viscosity. When testing the extensional viscosity of a polymer that's containing long chain branching structure, you will observe this extensional viscosity curve shows a strain hardening effect. So from these results, people defined a parameter that's called Troughton ratio. Troughton ratio equals to polymer's extensional viscosity divided by its steady shear flow viscosity. For a linear polymer, Troughton ratio should equals to 3. For measuring a polymer that's containing long chain branching structures, the Troughton ratio should be greater than 3. Next, let's move on to talk about how do we use rheology to study thermosetting curing. First of all, what geometry we shall use. Since this kind of sample is eventually going to cure, you need to consider to use a disposable parallel plate. The 25 mm and 8 mm disposable plates are the commonly used geometries for this kind of studies. Regarding test method for monitor curing, most of the time, people use an isothermal time sweep to monitor sample cures at an isothermal temperature condition. People also can program a temperature ramp curing to monitor sample cures with a ramping temperature. Also, you can program a temperature profile, something like a temperature ramp followed by isothermal to mimic a real processing condition. So during this curing measurements, the property we can monitor is we can monitor sample's viscosity and moduli change as a function of curing time or curing temperature. Also, we can study sample's gelation, measure gel time or gel temperature. If anyone who is interested to learn more about how rheology can help to study thermoset curing, we have a very helpful thermoset webinars that is on our website. So please feel free to log on to TA Instruments website and take this free webinar. This diagram summarizes the chemical reaction of a thermoset curing. So basically, the material starts from small molecules or short-chain oligomers in a liquid form. By adding a crosslinker or initiator, the reaction starts. The system starts to build its molecular weight. It goes from small molecules to oligomers to branch polymers and then highly branched polymers. At a specific time, when the first cross-linking network is created, the system forms a gel and completely loses flowability. This is what we typically call gelation. At this critical time, the viscosity of the sample goes to infinite. After gelation, the cross-linking reaction still continues. The material undergoes a vitrification and builds its mechanical strength until it forms a hard solid. So from stage C to stage B, you will need to use an oscillatory test method to continue monitor the material's mechanical property change as a function of temperature or time. Here is one case study to monitor isothermal curing of a 60-minute epoxy sample at 80 degrees C. The sample was loaded onto a 25 mm disposable parallel plate geometry. An isothermal time sweep test is conducted at an oscillation frequency of 1 Hz and using a small strain that's in the linear viscoelastic region of this sample. From this test results, we can see that at the beginning of the reaction, the sample's loss modulus is greater than storage modulus. That means the sample initially behaves like a liquid. Both moduli increase dramatically with reaction time. At a specific time of 204 seconds, this sample undergoes a liquid to solid transition. Beyond this point, the sample's storage modulus becomes greater than loss modulus. That means this sample behaves solid-like. After that, both moduli and complex viscosity continuously increase until eventually the sample is fully cured. Most of the time, when people studying thermoset curing, they would like to use their specific temperature profile that is mimicking their real processing condition. Here is an example of showing the thermoset curing using a temperature ramp followed by isothermal procedure. So we load the sample at the initial measurement temperature, and then we're conducting a temperature ramp up test. During heating, initially, both samples' moduli and complex viscosity decrease with increasing temperature, and then until it reaches to a minimum point. This minimum viscosity temperature is an important factor. This is the highest temperature you can use to processing this uncured resin. Beyond this point, sample starts to cure. Both moduli and viscosity increase significantly with increasing reaction time and temperature. From these results, we can also observe a G', G" crossover, and after that, both moduli continuously to increase until eventually the reaction finished. The gel point is a critical parameter in the thermoset curing process. At this gelation point, sample shear viscosity goes to infinity. The system loses solubility, and the molecular weight of the sample goes to infinity as well. In general rheological measurements, people empirically like to use this G', G" crossover point and define this point as the gel point. However, in the 1980s, Professor Henning Winter had found out that with most of the curing systems, this is not the true gel point, because the measured G crossover point is frequency dependent. This data is showing the thermoset analysis conducted using 3 different frequencies. From these results, you can see that the G crossover is occurred at 3 times. Therefore, Professor Henning Winter recommended to use a more precise way to describe the true gel point of a cross-linking system. In his method, he recommended to conduct the curing analysis using multiple different frequencies. After the test is finished, plot sample's tangent delta versus the reaction time. and the crossover point in the tan delta curve is defined as the true gel point of this system. However, most of the time, especially in industry analysis, people still prefer to simply just conducting the curing analysis using one single frequency and taking this G crossover, consider that as the gel point. For relative comparison purpose, this measurement is still valid. Most of the time, when the polymer cures, it shrinks. The amount of shrinkage could cause cracking or delamination to the end product. Using rheological measurement, we can actually monitor and quantitatively measure the amount of shrinkage. There are two ways you can use to monitor this shrinkage. First, if we hold the measurement gap constant, then during curing, you can actively monitor how much force is built up across this between the parallel plate. Here is the results of measuring a UV-initiated curing of an acrylic sample that is used in electronic circuit board. From these results, you can see that the amount of shrinking force built up across a 20 mm diameter parallel plate is as high as almost 15 Newton. The other method to measure shrinkage is to quantitatively monitor the dimension shrinkage. During this measurement, we can move the instrument head actively to release the shrinking force to zero. From there, we can then actively measure how much the sample gap changed during curing. For unfilled polymers, the cross-linking density can be quantitatively calculated using either a rheology or DMA measurement. Here is the equation of how to calculate the molecular weight between cross-linking networks, using the modulus that is measured under the rubbery plateau region. Then from here, we can quantify the cross-linking density using this equation. In a rheological analysis, not only we can study curing with a changing temperature or time, we can also study curing under a certain circumstance. This slide demonstrates using a rheometer to monitor curing initiated by UV light. These are 5 dental materials with different formulations. Using rheological measurements, we can quantitatively compare which formulation cures faster, how fast, and also which formulation will eventually reach to an ideal mechanical strength. TA Instruments Discovery Hybrid Rheometer is also equipped with a humidity chamber. This humidity chamber allows rheological measurements to be conducted with both temperature and humidity control. Here is an example showing the measurement of a silicon caulk curing under different humidity environment. The results clearly shows that this caulk sample cures much faster with higher environmental humidity. In this last section, we would like to talk about how to measure the rheological properties of a polymer solid. To measure a solid sample, you can choose to use either the torsional geometries or one of these DMA geometries. For Aries G2 user, the DMA test mode goes standard with all other tests. But for Discovery Hybrid Rheology users, you need to purchase a software key to enable this DMA test mode. In the torsional test, the deformation is applied under shear mode. So the measured modulus is defined as G. In the DMA test mode, the applied deformation is in linear mode. So the measured modulus is defined as E. E and the G is linearly related. And here is the equation that describes their relationship. In this equation, the nu here is the Poisson's ratio of your sample. The dynamic temperature ramp test is the most popularly used rheological test method to measure the properties of a polymer solid. Here is an example data of showing a dynamic temperature ramp test results on a solid polystyrene sample. This test is conducted under torsional mode, so the measured modulus are described as G. During this measurement, we can monitor the sample modulus and damping factor change as a function of temperature. Within this measurement temperature window, there is a glass transition which is observed at temperature around 100 degrees C. In the dynamic temperature ramp experiment, glass transition can be described in 3 different methods. The first method to describe glass transition is by taking the onset value of the G' curve. This temperature usually occurred at the lowest temperature. The second way to describe glass transition is by taking the peak value of the loss modulus. And the third method to describe Tg is by taking the peak value of the 10 delta peak. This rheological temperature ramp method is most sensitive for the measurement of polymer chain relaxation and polymer transitions. For the glass transition measurement of a highly cured or highly filled system, using this rheological method is a lot more sensitive compared to use a DSC method. In addition to measuring glass transition, this rheological temperature ramp test is also sensitive to measure all subambient beta-gamma transitions in polymers. Those subambient transitions are mostly associated with some local chain or side chain relaxation. Measure these subambient transitions can help us study the impact strength of a material. Here is an example of using the DMA mode to conduct a dynamic temperature ramp experiment on a PET film sample. From these measurement results, we can see that the glass transition of this sample is observed at 85 degrees C. Under subambient conditions, we can see another weak and wide transition which has occurred at temperature about minus 72 degrees C. This transition cannot be measured using a DSC method, but we can see this transition clearly from this DMA measurement. Here is a list of all the properties we can measure using rheology on polymer solid. We can measure a polymer's glass transition and secondary transitions. For polymers which are partially crystallized, we can use rheological measurements to differentiate their degree of crystallinity. We can also measure polymers with different cross-linking and measure phase separation in polymer blends. We can also study the differences in their mechanical properties in polymer composites, study aging influence to a polymer, measure curing of a network, study the polymers with different orientation, and also we can measure the effect of additives such as plasticizer to the physical properties of a polymer. In our DMA applications training courses, we provided a lot of detailed examples to show you how to perform a rheological measurement to study these properties. Before we end our today's course, I would like to show you where to find all the help documents. After you install Trios to your computer, you should be able to find this icon from your desktop. Double-click on this icon, you will open this TA Instruments menu. From this menu, you can find a lot of useful information and getting started guide on how to operate the instrument and also how to use some specific accessories. After you open Trios, when you double-click on this big green question mark, you will open this Trios Online Help menu. You can search this online help by typing in some keywords, which will allow you to find the topic of your interest a lot faster. In addition to this theory and applications training course, from our website, you can also find some web-based e-training courses. We have an e-training course on Aries G2 rheometer. We have an e-training course on Discovery Hybrid rheometer, and also a course on Trio software. Those e-training courses are mostly focused on basic introductions on how to operate the instrument and also how to use the software. We also have practical series of training courses in thermal, rheology, and also microcolorimetry. These series of courses are mostly focused on discuss the theory in thermal and rheological technique. In addition to training courses, you can also find some very helpful webinars from TA Instruments website. Many of those webinars are given by professors from different universities. The topics are specifically focused on their research projects. For example, this webinar is talking about interfacial rheology, And here is a webinar talking about colloid rheology, and this is a webinar talking about rheology in polymer processing. Also, on our website, you can find hundreds of helpful tech tips. Those tech tips are short YouTube videos teaching people how to operate the instrument, how to properly attach a geometry, calibrate a clamp, how to load a sample, or how to set up a specific experiment. In our applications note library, we have hundreds of short applications note papers. Searching by keywords, you can easily find some of the papers that's related with your research. On our website, we also have a series of Instant Insight seminars. These seminars are discussing analytical techniques in different applications. With that, I would like to end this training course for today. Thank you for attending this course, and I hope you found it informative. All of your questions can be submitted to this email box. You can download the content of this presentation from this following website. In addition to this theory and applications rheology training course, we also offer some other online courses, including TGA, DSC, and DMA. Again, thank you very much for attending this training course. Have a great day.